Okay, so hi everyone. In this video, I am going to discuss about deleting a certain node in a binary search tree. And in the last video, we discussed about BST insertion. So if you're interested, you can watch the previous video that I have uploaded. So let's proceed. So let's say we have deleted a node in the binary search tree. So if we remove any node there are so many cases that we have to consider. And deleting a node, just like in insertion, we have to maintain the binary search tree na property. So what's that binary search tree na property again that we have discussed? So essentially, for all of the nodes V in the tree, so its right subtree should na keys should have values greater than the left na subtree. Okay? So that should be true for all the nodes in the tree, except the leaves, of course, where it doesn't have any children anymore. Okay, so now compared to searching or insertion, deletion is not as straightforward. So there are some cases that we have to consider. But the first step would be to locate its parent or the parent of the node that we want to delete and itself in the tree. So these are the cases that we have to consider because as we mentioned here, there are a number of different cases that we have to check. So first one is, what if we are deleting a node that doesn't have any children? So if that's the case, then we just have to remove it and assign null to its parent reference. But what if the node that we want to delete has one child? So what we can do is replace the node with its subtree. And the last case that we have to consider is, which is the most tricky of all, is that the node has two children. So what we can do here is to replace the node with its either its predecessor or with its successor. So depends on the implementation. So when I say predecessor, so it's the rightmost node of its left na subtree. But when we say it's the successor, it's the leftmost node of its right subtree. So later you will see how it is done. Okay? So if that node has a child, then it can have at most one child. Then what we can do is attach that to the node's parent. So let's see. So this is the case wherein the target is a leaf, or the first case here where doesn't have any children. So this is the same tree that we are using, like in the previous example. So the root is 47, and as you can see, all of the items in the right subtree is greater than the items on the left subtree, and it's true for every node. Okay? So we want to delete 30, and we can see that 30 is here. Okay? So what we have to do is to look for 30. Now we know that 30 is 30 is less than 47. So we are going to move to the left and we are going to compare again. So 30 is less than 32. So we are going to go to the left. Now we are at node 19. So 30 is greater than 19. So we are going right. So we are now at 23 and 30 is greater than 23. So we are going right. And we have found the node 30 and then we are going to delete that node. All right. Now, another case of deletion is, what if that target or the key that we want to delete has one child? So for example, we want to delete 79. Where is 79? 79 is here. Okay. And as you can see, it has one child, which is 96. So what are we going to do here? So we are going to replace it with its subtree. And 79 has this subtree rooted at 96. Okay, so what we are going to do is we are going to replace it with a subtree. So locate its parent. The parent of 79 is 63. So we are going to link 63 with 96 and then remove the link of we are going to link 63 with 96 and remove the link of 79 between 63 and then 96. And now we have the new binary search tree maintaining its property with 79 deleted. Okay, so here's after deletion. Next is we have this tree again and we want to delete 32. So where is 32? Yeah, this is 32 on the left of 47. Now, as I mentioned, this is another case. This is the most tricky part of all. And there are two implementations. One would be to replace the node with its predecessor or the rightmost node of its left subtree, or we could go with its successor, the leftmost node of its right subtree. So assuming that we have implemented replacing the node with its successor. So in that case, we are going to look for the leftmost node of its right subtree. So we want to delete 32 and we have to check where is the right subtree. So the right subtree would be this part where it's rooted by 41. And we mentioned that with the successor, the successor is the one on the leftmost node, and the leftmost node is 37. Again, successor is the leftmost node of the right subtree, and the right subtree is this part, and leftmost node is 37. So we are going to replace 32 with 37. Okay? So this would be temporary. And then what can we do now is we set this as temp and then temporary in a node, and then we detach it from the tree. And then what we are going to do is attach target node's children to the successor. So the children of 32 are 19 and then 41. So instead of being attached to 32, 19 and 41 would be attached to 37. And also, make successor child of target's parent. So the successor is 37 and the target is 32 and its parent is 47. So now this 47 must be linked to 37. And now we can remove all the links of 32 from its children as well as its parent. Okay, so understood? So if it has two children and we are looking at the successor, then we are going to look at the leftmost node of, here as a review, leftmost node of its right subtree, okay? And then this is the successor now, and then we are going to attach target node's children, and 37 is attached to 41 and 19, and make successor child of target's parent, in this case, with 47, and we can remove 32. Okay, next is, so just a little note here, that was a bit easy because the successor, which is 37, did not have any subtree. Okay, now let's look at another example. So assuming that we are going to make use of the predecessor instead. So in other words, if we are deleting a node that has two children, and then we are choosing the predecessor. So when we say predecessor, it's the rightmost node of its left na subtree. Okay, so let's say we are going to delete 63. Okay, 63. And since we are looking for its predecessor, the rightmost node of the left subtree. So what is the left subtree of 63? It's this part, this whole tree, which is rooted at 54. Okay, so now using the subtree, what is the rightmost na the leftmost the rightmost node rather? So that would be the rightmost node is 59. Okay? So this is the left subtree of 63, and we are going to look at the rightmost node, and it's 59. But as you can see, 59 has a subtree. So what are we going to do here? What are we going to do? Unlike earlier that we just have to exchange the two nodes, the target node and then the temporary node, and then do the necessary attachments. But in this case, 59 has a subtree. So what can we do here? So what we can do is to attach the predecessor subtree to its parent. So what is the parent of 59? It is 54. And the child of 59 is 57. And we are going to attach the child of the predecessor, which is 59, to the parent of 59. So in this case, 57 is attached to 54. Okay. Next is we are going to attach the uh, subtree. So now we have the 59, which is the temporary, and then we are going to replace 63 with 59. So that means that all the children of 63, which is the left subtree 54, and then 79 must be connected to 59. Okay? So 59 connected to 79, and 59 to 54. And next is we are going to attach the subtree. Then we have to attach the children, and then after that, attach the predecessor to target's parent. So the parent of 63 is 47. So therefore, 47 will be attached to the predecessor, which is 59. And then we can delete references from 63, and we are done. Okay? So just a little clarification, not clarifications, you can either choose the successor or the predecessor. So in this example, we chose the successor, wherein we look at the right subtree of a certain node that we are going to delete, and then on the leftmost node, and do the necessary stuff. And if we do the predecessor, then we look at the rightmost node of the left subtree. But if the predecessor has a subtree or a child attached to it, then we have to do some necessary things like attaching its children to its parent and doing the same thing like what we did earlier with the successor example. Okay. So the efficiency of a BST binary search tree operation depends on the height of the tree. So all of the three operations like the search, insert, and then the delete are O of height. And if the tree is complete or full, then then it would be the floor of log of n plus 1. Okay. So what happens if it's not complete or full? So let us see in the next video, we are going to discuss that.